Okay, so welcome to Math 310, Introduction to Modern Algebra. This is lecture 16. We're going to do more ring theory, but I wanted to just do another riddle problem because these are great ways to talk about how should you look at mathematics, how should you attack a problem, and then take that knowledge and try to connect it to some of the material we've seen before. So the problem, slightly rephrased, is you have 100 mathematicians standing in a line. So these are intelligent people. If there is a way to figure out something, they will do it. And each person can only see the people in front of them. So the first person sees no one, the last person sees 99. The hats are either white or black, and they are put on by an evil professor. So I get to hear your strategy. Whatever I can do to make things go wrong, I will do so. And each person speaks at a predetermined time. So at the very start, the 100th person says either white or black. 1 second later, the next person says white or black. 1 second later, the next person, and so on, and so on, and so on. Whenever you speak, if you speak correctly, there's lots of ways to do this. We either add $1 million to the pot or you survive. Let's do the $1 million. And we want to maximize the number of people who speak correctly. So when you speak, you have a choice. Are you trying to say the color of your hat, or are you trying to pass information on to other people? So we talked a little bit about last time that you should never, ever, ever try to solve a problem like this as given. You should not try to look at it with 100 people. You should first try something much easier. And rather than looking at 100 people, let's start off with simpler cases. So we did the case of just one person, and we realized if there's just one person, there's nothing we can do. If there's two people, well, things are actually a little bit better now. And so what we can do is we can have the second person say the hat color of person in front. And this leads to 50% being correct. And of course, we could easily extend this to if we had more people, then 2 says the color of 1.
We can't see your screen.
Oh, you can't see the screen? It's not showing. All right, thank you. Let me try again. Okay, is it displaying now?
Yes.
Okay, perfect. All right, so sorry about that. So fortunately, we were just reviewing what we did last time. If we have 4 people, then we can just keep this pattern going. And person 4 would say the color of person 3. And so by continuing like this, we can easily get to 100%. So my question for you was not just what's the best you can do. Can somebody give me a strategy that would get 66%? Any thoughts on how to do that? So remember, person 3, let's make them different colors. We'll make person 3 red, we'll make person 2 green. Person 3 can see 1 and 2. Person 3 can see 2 and 1. And person 2 can see person 1. So there's different amounts of information. So when person 3 speaks, they can pass on some information. So what are the possibilities for 1 and 2? They could both be black hats. It could be black-white. It could be white-black, or it could be white-white. I like to do it in an order like this to make sure I don't miss any possibility. So notice that person 2 knows person 1's hat. And so if person 3, we could have them say black if both the same color, and white if both different colors. When you say this, 2 knows what color 1's hat is. And 2 now knows, do I have the same color or not? So this is going to lead to 2/3 correct. Did anybody have anything like this? So I will leave as a challenge, can you do 3/4? So here is a way to do 4/5. So imagine we have our hats again. So we have 1, 2, 3, 4, and 5. So I think this works. And again, I like the idea of having different levels of solutions, of not necessarily getting to the best answer immediately, but can we make things a little bit better? So there are two possibilities for these two hats. They're the same or they're different. If you know they're the same, do both people know what hat colors they have?
Yes.
Yes. If they know they're the same, if 2 sees a white hat, then 2 knows they have a white hat. If they see a black hat, they know they have a black hat. So as soon as 1 and 2 know that they're the same, they both know their hat colors, 2 first and then 1. If they know they have different hat colors, 2 is different than what 1 sees, and as soon as 2 speaks, then 1 knows. Similarly, for 3 and 4, they're both the same or different. Agreed? So we have 2 cases where they're the same. These 2 cases are the same. I'm sorry, these 2 cases are the different. And then we have 2 cases where they're the same. So what could person 5 say to help 1, 2, 3, 4 figure out what they have? So this is the idea of propagating information. So 5 can say black if both pairs have the same parity, and white if different. So let me just draw this a little bit larger. Or not. So when you look at the first 2, they're either the same or they're different. And when you look at 3 and 4, they're either the same or they're different. So person 5 will say black if it's same, or here. Let's go through all the possibilities, very carefully. So same, same, different, different, same, different, different. And person 5 is going to say black if they're both the same by same, or both different, different. And if they have opposite, she'll say white. So imagine, to make things explicit, let's say I give you black, white, white, black. In this case, these are different. These are different. So what would person 5 say?
Black.
Black. So person 5 says black. And because they say black, now let's look at what person 4 is going to do. Person 4 sees that the 2 in front of them are different, and they know that they also have to be different. So since they see a white, we now know person 4 is going to say black. Person 3 knows that they're different than person 4, so they know they have to say white. people's 1 and 2 know that they have different hat colors. Since person 2 sees a black, they know they have to have a white. And so by doing this, we are actually able to get 4 out of 5. Notice we did not get 3 out of 4. So I will leave as a challenge problem. Can you come up with a way to get 3/4? So sometimes certain fractions are easier to work with than others. Certain cases are easier to do than others. We talked about this, sometimes in the past, after you do 1, 2, is the next case to try 3, or is the next case to try 4? Depending on what you're doing, sometimes it's easy to go 1, 2, 4 than 1, 2, 3. I'll just end with, does anybody know how to get in the limit 100% in the limit? A 100% doesn't mean everyone. It just means that as the number of people goes to infinity, the percentage goes to 100. Does anybody know how to get 100%? I know at least one person does. Somebody told me yesterday they know how to do it. How can you get almost everybody in the limit? You can get all but one.
And then each subsequent person can see whether they see an odd or even number of black hats, and they can deduce whether they have a black hat or a white hat.
Okay, your audio missed out in the beginning, but I did hear the end. So last person says black if we have an even number of black hats, and white if have an even number of white hats. Since the number of black plus the number of white equals 99, exactly 1 is even. So what's really going on here is this is a parity observation. So you're basically just saying black if there's an even number of black hats, white if there's an even number of white hats. Now everybody knows that, and they can just adjust. So if you say 100 says black and 99 sees 34 black hats, what color hat do they have? So person 100 says black if they see an even number of black hats. They say white if they see an even number of white hats. Person 100 said black, so we know that they see an even number of black hats.
One should be odd, I guess. Yeah, you wrote even.
I'm sorry?
You wrote if have even numbers. So you wrote even number.
Well, right. So you can't have an even number of
No.
black hats and an even number of white hats because there's 99 hats that person 100 sees. The last person sees n minus 1 hats. In this case, they see 99 hats. Right?
Yeah, so it should be white. So 99's hat should be white.
It has to be white because if it was black, then person 100 would have seen an odd number of hats. So 99 has a white hat. And this just propagates down. And so you can actually get all but one. I'll leave just as an interesting remark, there's another way you can get 100% in the limit. N minus the log base 2 of n, something like that. What you can do is write the number of black hats in binary. Have B equals 1 and W equals 0. Use the last, basically, log base 2 of n people to say the number of black hats, person n sees. So there's a lot to think about for this problem. If you are going to be a teacher, there's a lot you can do in classrooms with something like this. The real issue is parity at the end. It's the simplest way to look at it. At the end of the day, we just care about, the equivalence class. Are you an even or an odd? And this was one of the big things we looked at when we were doing clock groups. We were looking at equivalence classes of numbers. And this is just a really great way of doing it. The other thing is we have intelligent people. You don't have to have the last person doing all the calculations. Each person can do calculations as it goes on. This is used in a lot of stuff that goes on in the background in your daily lives. When you're streaming information, when you're sending stuff like this, you don't have to send the value of every pixel. You can send code compressions and then have the computers on your end, on your phones, computers, whatever, expand it outward. And so this is a really important idea of using the various constituent pieces to do calculations, to do computations. All right, so this was just a really good way to talk about parity. So let's shift back now to rings, and we'll try to finish up chapter 3, and then talk a little bit about a nice application of this to vector spaces. So we'll say R is a commutative ring. I'm sorry, we'll take a commutative ring R, and we'll say an ideal of R is a non-empty subset that has two properties. If A is in the ideal and B is in the ideal, then A plus B is in the ideal. And if A is in the ideal and R is in the ring, then R times A is in the ideal. Does this remind you of anything that we've seen before? So where have you seen something like this before, where we have an object and we're looking at a subset of the object?
Rings and subrings, maybe?
So rings and subrings, and go earlier than rings and subrings.
Subgroups.
Groups and subgroups. This is a really common theme. So similar to rings and subrings, groups and subgroups. Looking at subsets of items of interest. The first property seems basically it's closed under addition, right? What about the second property? Is it closed under multiplication? So do you think it's closed under multiplication?
I don't think so.
So that would mean if we have A and B in I, must A times B be in I? Well, the second property says if A is in I and R is in R, then R times A is in I. And again, because it's commutative, this is the same as AR is in I, because it's commutative. So is there a choice of R that would imply AB is in I if A and B are in I? So can you find a choice of R such that A is an I, R is an R, and then AB is an I? What should we take R to be?
The identity?
Not the identity. We want to show A times B is an I. And we know that whenever A is an I, no matter what R we take, RA works. So what should we take for R if we want to try to show that AB is an I? So we don't have that many objects that we're looking at. We have A, B, we have the zero, we have the identity. What should we try taking?
B?
B. So take I equals B, and we get, AB is an I, can do as I is a subset of R. So it's going to be closed under multiplication because I is a subset of R. It's more than it's closed under multiplication. It's if we multiply by anything in the ideal, we stay in the ideal. So it's possible that, if I take A and B in the ideal, the product is in the ideal. But if I take something that's not in the ideal, maybe the product is not in the ideal. Nope. To be a ideal, you have to be in the ideal with any product. So it's a much stronger condition. You do get closure. So again, whenever you see stuff like this, you always want to ask, what are the consequences? I think you might want to ask, why are they defining it like this? What's the advantage of something like this? So let's look at special types of ideals. The first one we're going to encounter is the principal ideal generated by C, and there's two different ways to denote it. We could denote it either C times R or C in parentheses, and it's the set of all multiples of C. So let's check and see, is this an ideal? So is this an ideal? So we have to show two properties. So if A and B are in C, then what does it mean for them to be in C? Then they have to exist, let's call them R sub A, R sub B, such that A equals RAC and B equals RBC. Then A plus B would be RAC plus RBC. And what does that equal? So how can we simplify this sum?
RA plus B bracket C.
RA plus RB. And why were you able to do that?
Because it's distributive.
Right, so now we're using the distributive law. And this is going to be in C as RA plus RB is in R. So let R equal RA plus RB, and thus thus A plus B would be R times C. So because R is a ring, RA plus RB is in the ring, and we're done. So that's the first point. The second point is if A is in C, then for all R in R, RA has to be in C. Well, as A is in C, there exists an element, let's call it R tilde, such that R tilde C equals A. Thus, RA is going to be R tilde A. By associativity, this is just call it maybe R hat A, where R hat is R tilde is in the ring because the ring is closed under multiplication. And thus, we do get that RA is in the ideal. So this is a good definition. It is an ideal, and it turns out that these are going to be very useful ideals. Anybody have a thought about what might be a good choice of C? Any thoughts about what might be a good choice of C? There should always be two natural choices to try.
Maybe the identity.
Which identity?
Either the additive or
Either,
multiplication.
exactly.
Oh.
So if we take the ideal generated by 0, that's just going to be 0. And what do you think we would get if we take the ideal generated by 1? So this is going to be all elements of the form R times 1, where R is in the ring. So what would this equal?
The ring itself.
The ring itself. So you always have, two trivial principal ideals. This should be very familiar to what we were seeing when we looked at groups, that you have some extreme cases that you can look at. And now the question is, well, can we find something more interesting to look at? And so rather than looking at these trivial cases, can we find something non-trivial? So to do that, we need to choose a ring. So one of the best rings to look at is either the clock group or all the integers. So let's look at the integers. Okay. And so anybody have a choice for C that we might want to try? Anything but 2 numbers should be good.
2.
2. So we could look at, this is going to be all multiples of 2. So ... -4, -2, 0, 2, 4, ... Any other good choices? What should we do after 2? So what would be a good thing to try after 2?
3.
3. And then that will give us all multiples of 3. Let's see, -6, -3, 0, 3, 6. Now things are interesting. What would you want to do next? I think there are 2 good natural choices.
Try to generalize.
Right, and so what should we look at next? There are 2 natural things to try next. We did 2, we did 3, we should do
4 or n.
one possibility is 4. I claim that there's another number we might try instead of 4. We did 2, we did 3. What do 2 and 3 both have in common?
They're prime.
Prime.
They're prime. So again, this is going back to the hat riddle, going back to what should we do next? Now again, no matter what number I give you, if I give you n, it's just going to be very simple. Minus 2n, minus n, 0, n, 2n, dot, dot, dot. But maybe these ideals have different properties depending on whether or not their generator is prime or composite. If I give you two numbers, you can add them and you can multiply them. We might want to do the same thing with ideals. What happens if we add ideals? What happens if we multiply ideals? What do we get? And so the whole idea is to try to generalize from the integers to more interesting settings. And if you continue in higher mathematics, these play a huge role. So, my job right now is to just give you a little bit of a sense of what's on the radar. So for this problem, it doesn't really matter what we look at. You give me any number n, the principal ideal generating the integers is very easy. We could look at more interesting situations. So, again, the ideal generated by C is going to be all multiples of C. We could look at more interesting examples. Let's take, R to be polynomials with integer coefficients of finite degree in X. So we will often write this as Z, square brackets X. And this is going to be all polynomials of the form, an x to the n plus dot 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 plus a1x plus a0. Each ai is in Z, and n is a non-negative integer. So this is a great example of a ring. And you can see that if I take two polynomials of finite degree and add them, it's a polynomial of finite degree, and the coefficients will still be integers. If I multiply them, it'll still be a polynomial of finite degree. The coefficients will still be integers. And so let's try to look at a principal ideal. Can somebody give me a polynomial of the variable x?
X.
X. So if you give me x, then this is going to be all things of the form r times x, where r is a polynomial of finite degree. So this is going to be all polynomials with 0 constant term. And a natural question might be, what if I give you a couple of elements and ask, what's the smallest ideal that contains them all? If I give you a finite number of elements, is there always going to be an ideal that contains them? So if I give you, say, a1, a2, dot, 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 an in R, is there always an ideal containing them? What do you think? Is it possible to find an ideal that contains them?
The ideal generated by 1.
Good, and that's just the whole ring, right?
Yeah.
So there's always, we can always find an ideal. So is there something smaller? And that's not clear. And so one of the things we're going to want to do is to try to figure out how can we combine ideals, how can we find ideals that contain given elements. All right, so another definition, let R be a commutative ring, and let I be an ideal of R, so it has those two properties, then for each element A in R, the coset of A is the set A plus I is all numbers of the form A plus C, where C is an I. So this should remind you of cosets we saw with groups. And so if I take an element X in A plus I and Y in A plus I, must X plus Y be in A plus I? What do you think? In other words, do you think that this is an ideal? What do you think? Should we gather some data? So let's try to find an example. Let's take R to be Z, and we want I to be an ideal. Let's take I to be the ideal generated by 12. Okay. So A plus I would be all numbers of the form A plus C, where C is in the principal ideal generated by 12, or in other words, this is all numbers of the form A plus 12M for some M. Does this look familiar? This is just our old clock friend. So what are the distinct possible values for A that we should be thinking about?
0 to 11.
0 to 11. So we'll study A in 0 to 11. Note, 13 plus the ideal generated by 12 is the same as 1 plus the ideal generated by 12. So you should be able to prove that. This is very similar to cosets with groups, that we have the ability to choose a representative. So without loss of generality, our representatives, live in the set 0 to 11. So do we think that if we take two different elements, X and Y, in one of these cosets, that their sum is in the coset? So somebody give me a choice for A. What's a good choice for A? Any choice but one is going to work. So give me a choice.
3.
What did you say?
3.
3. Okay, so if A equals 3, then I want an X in 3 plus multiples of 12 and Y in 3 plus multiples of 12. So can somebody give me an X and a Y? So I need an X that's in 3 plus multiples of 12.
15.
15. What's a Y that works?
27.
27. And X plus Y is going to be 15 plus 27, 20, 30, 42. And 42, let's see, 12 times 3 is 36. So it's 6 plus 3 times 12. So this is in 6 plus the ideal generated 12. It's not in 3 plus the ideal generated by 12. So if I give you a coset, it's unlikely that two elements in the coset are going to be in the same coset. But no matter what x and y I take, x plus y is going to be in the same coset. They're always going to be in the coset 6 plus 12. Okay, so now we can talk about prime ideals and maximal ideals. So these are going to be a little bit different than regular numbers. So as always, R is a commutative ring. An ideal is called a prime ideal if it's not the whole ring, and if whenever a product of elements is in I, then either A is in I or B is in I. So we observe that if I is a prime ideal, then it has the following property. If you take two things that are not in I, then their product is not in I. Okay, so again, these are definitions. They should hopefully be useful definitions. What do you think this might be? What do you think prime ideals might be attempting to generalize? If you had to guess, what do you think a prime ideal is trying to generalize? Oops. Let's put it in. So what do you think a prime ideal is trying to generalize from numbers?
The prime numbers?
The prime numbers. So that maybe this is a generalization of prime. That, for primes, we had, if a prime divides a product, it divides one of the two factors. And a prime ideal, if you ever have a product of elements in I, then either A is in I or B is in I or both. Or another way of saying it is if you have two things that are not in I, their product is not in I. So we'll go back and we'll do maximal ideal in a second. So let's do prime ideal. We'll use the funky writing. So let's go back for our example to the ring of integers z. And let's look at multiples of n. So minus 2n, minus n, 0, n, 2n, dot, dot, dot. Let's take n equals 12, and let's take n equals 7 and see the differences. So minus 12, 0, 12, dot, dot, dot. Minus 7, 0, 7, dot, dot, dot. And so I'll just put this over here. So there's the definition of being a prime ideal. If you have a product in the ideal, then either A is in the ideal or B is in the ideal or both. Do you think 12 is a prime ideal? So is 12 a prime ideal? If whenever a product is in 12, is at least one of them in 12? What do you think?
No.
Okay, so give me a reason why it's not a prime ideal.
3 times 4 is 12. That's in the ideal.
Good.
But 3 is not. 4 is not.
Great. 3 times 4 is in 12, but 3 and 4 are both not in the ideal generated by 12. And 12 is a composite number. Is 7 a prime ideal? So hopefully the answer is yes. So if we had A times B is in the ideal generated by 7, then there exists a R such that AB equals 7R, as 7 divides 7R, that implies 7 divides AB, and thus 7 divides A, or 7 divides B. And we see that there was nothing special here about the number 7 other than that it was a prime. So we've actually just proven the following. Proved the principal ideal generated by P is a prime ideal if P is prime, and is not a prime ideal if N is composite. We did the special case when N equals 12, but the argument holds in general. So at least this is a good name. A prime ideal is in some sense acting like a prime number. It's not exactly the same, but so that was the first part. The second part was an ideal, let R be a commutative ring. An ideal is called a maximal ideal if it's not the whole ring, and there are no ideals properly contained between I and R. So in other words, if I give you the ideal I, it has to live inside R. If you tried to find something J between the two of them, then either J equals I or J equals R. So maximal means there's no way to put an ideal above it, that contains it, without being everything. So let's copy this again. So let's do an example again. So let R be the integers. Is N maximal? And if so, for what N? So what would be a good N to try first?
One.
1. Well, if we take N equals 1, then you get the ideal generated by 1, which is all of Z. So in our definition, it says I is not allowed to be all of R. So we can't take N equals 1 because this is all of R.
2.
Right. So this is all of R equals Z. So you could try 2. So this is now all multiples of 2. So dot 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 -4 -2 0 2 4 dot dot dot. So the question is, we have the ideal 2, we have the integers, and we want to try to find, is there an ideal between 2 and all the integers? Is there something that contains everything in the ideal generated by 2, all the even numbers, and something else? And we want that not to be all of Z, and we don't want it to be all of 2. So if 2 is maximal, then the only J that work, J equals 2, and J is everything. So let's prove that no other j work. So proof only j equals 2 and z work. So assume j does not equal 2. We must show it's everything. We must show j is everything. As j contains 2 and j does not equal 2, must have some x in j with x not in 2. So what would it mean for x to be in j but x not to be in the ideal generated by 2? What does this tell us about x? So the elements of 2 are the even numbers, and we're telling you there's some number in j that's not in the ideal generated by 2. So what must be true about it?
It needs to be odd.
X must be odd. Thus, x is odd, so there exists an m such that x equals 2m plus 1. As 2m is clearly in 2, by additive closure, x, well, I'll do, I guess, negative 2m is in 2. X minus 2m, which is x plus negative 2m, has to be in j. Right? So this is going back to what is the definition of an ideal? Okay, here we go. So an ideal is a non-empty subset with the following two properties. If two things are in the ideal, so is their sum. Oops. Okay, here we go. So it's closed under addition. So if j is an ideal, because x is in j and negative 2m is in 2, which is in j because j contains 2, x minus 2m has to be in j. But what does x minus 2m equal?
1.
1. So 1 is in j. So now, by multiplicative closure, r times 1 is in j. Thus, j equals r. So we've just shown that 2 is maximal. It's prime and it's maximal. Given that 2 is maximal, what do you think? What else do you think might be maximal?
The prime.
Yeah. Oh, this is what was confusing me. I put this page in the wrong order. Okay. That's why I was having trouble finding where to go because I put the maximal before the prime stuff. So maybe, so conjecture, P prime, maybe the ideal generated by P is maximal. So I'll leave that as an exercise for you to think about. You know, I'm sure it's in the book, but can you show that it's maximal or not? And maybe conjecture, if n is composite, maybe the ideal generated by n is not maximal. So here, let's say n equals a times b. So the question is, can you find an ideal? Just 1 second, I'm getting a call on my office phone. Just 1 second. Okay, hopefully it's still sharing the screen. Yes, okay. So can we find an ideal that's larger than AB and strictly smaller than R? And again, we're doing n is the product of AB. So there are two natural things to try. What should we try? What do you think might work?
Like a multiple of A or a multiple of B.
Right, so we should try the ideal generated by A or the ideal generated by B. And so we have to show now clearly everything is an ideal. So the question is AB contained but not equal to A? And is AB contained and not equal to B? Well, if we can show one of them, the other one is going to be the same eigenvalue. And so can you find something in A that's not in AB? And so A is just going to be the multiples of A. A 2A, 3A, dot, dot, dot. And then AB is going to be the multiples of AB. Minus 3AB, minus 2AB, minus AB, 0, AB, 2AB, 3AB, and so on. So can you find something in A that's not in AB?
A.
Good. So as A is in A, but A is not in AB, AB is contained but not equal to A. Now we have to show that A is not equal to R. Can you find something in R not in A? So R is going to be dot, 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 minus 3, minus 2, minus 1, 0, 1, 2, 3, dot, dot, dot. Can you find something in R that's not in A?
1.
1. So as 1 is in R, but 1 is not in A is contained but not equal to R. Thus, AB is not maximal. So it kind of makes sense. If we're looking at multiples of AB, multiples of A will clearly contain all of those. Multiples of B will clearly contain all of those. And they'll have some things that are not in AB. Similarly, multiples of A will be contained in the initial ring R, all the integers. But there'll be things that are missed. So this shows that if n is composite, n is not a maximal ideal. And I will leave you to ponder whether or not if P is prime, if P is maximal. We did the special case of, no, it was right, of 2. Does this argument generalize to any prime, or was there something special about 2? Okay, so then there's lots of theorems you can prove. And so, if R is a commutative ring and I is an ideal with I not equal to R, then I is a prime ideal if and only if the quotient ring is an integral domain. I is a maximal ideal if and only if the quotient ring is a field. And then every maximal ideal is a prime ideal. So we could spend a lot of time going through all the different properties of rings. I just want you to be aware of some of these right now. There are connections. So chapter 4, which we're not going to spend too much time on, is just revisiting linear algebra, revisiting what you've done on vector spaces. And so, vector space has 2 types of operations. We can multiply a vector by a number. This is the scalar multiplication. Usually the scalars are the real numbers or the complex numbers. Those are what you use most of the time. And we can add 2 vectors, and this is vector addition. And so a field, as we've said before, is a commutative ring with the property that every non-zero element is invertible. You can do vector spaces over more than just the reals and the complex. The reals and complex numbers are examples of fields. Every non-zero element is invertible. We could form vector spaces over fields. And so a lot of what you've done generalizes. When you guys did linear algebra, did they give you a formal set of properties of a vector space?
I believe so. Yes.
Okay. And so you can ask, how general can we be? So you might have done things only over the reals and the complex, but you can do things more generally. You want the scalars to come from a field so that you can invert. You want an identity, you want distributive laws, you want associative laws, you want a zero vector. And then sometimes it can be confusing. Are you talking about the zero vector or the zero number? And so if you look very carefully, this is in bold. And we often use bold to denote the vector. Sometimes instead of doing things in bold, sometimes people put an arrow over it to indicate that it's a vector. Either way is fine. And then, similarly, you can start to revisit a lot of the linear algebra, and we can talk about, linear transformation from V to W is going to be a function that satisfies the following conditions. L of the linear combination is the linear combination of the L's. So you might have seen a condition like this with subspaces, to detect if something is a subspace. So linear transformations are very nice. This is true for matrices. If I give you a matrix A acting on, say, C1V1 plus C2V2, this is the same as A C1V plus A C2V. And then since C1 and C2 are constants, I can just pull them outside. That should be V1, V2, C1A, V1 plus C2A, V2. So a good example of a linear transformation is, a matrix acting on vectors. And what's really nice about this is if we can understand what a matrix does to a basis, then we can understand what it does to anything. So these are really nice things to have. So what do we mean by a basis? So hopefully you've talked a little bit about this in your linear algebra class. We're not going to have, many exam questions or probably any exam questions or homeworks on this, but I just want you to be aware of how things fit together. So a finite basis is a finite set of vectors such that every vector can be written as a linear combination, and there's one and only one way of doing it. And so it turns out it's a big theorem that you can't have 2 bases with different dimensions. So if I give you R3, what's the dimension of R3? How many? Yes, it is 3. And the standard basis is E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. But you could also do, V1 is, 1, 0, 0. V2 is 1, 1, 0. V3 is 1, 1, 1. That would also work as a basis. They have the same number of elements. And so I could give you the set of all numbers of the form a plus b square root of 2 plus c square root of 3, where a, b, and c are rational numbers. I could give you something else. I could give you a plus b root 2 plus c root 3 plus d square root of 6. Where do you think the square root of 6 came from?
The multiple of 2 and 3.
Yeah, the multiple of square root of 2 and square root of 3. So if I only care about adding, so this is closed under addition. It's not closed under multiplication. Right? The square root of 2 times the square root of 3 is square root of 6. That can't be written in the form a plus b root 2 plus c root 3. So it's a nice exercise. Show there do not exist a, b, c rational such that the square root of 6 is a plus b square root of 2 plus c square root of 3. Now, if I look at the stuff on the other side, this is closed under addition and multiplication. Both of them, however, would be vector spaces. Because they're closed under addition, that's all that matters. You don't have to be able to multiply two vectors. It's nice if you can, but you don't have to. So your natural question is, what are the dimensions here? Okay, and then we'll just end with the finite field FP, which we've seen before. P is a prime. This is going to be the elements 1, 2, well, I guess 0, 1, 2, dot, 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 P minus 1 under clock arithmetic. And every non-zero element is invertible. This is a field. If n is composite, then 0, 1, 2, dot, 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 n minus 1 is not a field. All right, so this is a good place to stop for today. So we will continue with this on Tuesday, and then you should be able to do several of the homework problems by now. The homework is not due for a while, but you don't want to wait until the last minute to do it. And as always, if you have any questions, just shoot me an email or call, and happy to arrange a time to chat. All right, have a good weekend, all.
Take care. See ya.
Thank you.